High temporal resolution in cameras can enable devices to visualize and interpret the environment in different ways. Today, for high-speed photography applications, consumers would need very expensive, bulky or multiple cameras. We envision a future where ubiquitous mobile phone cameras in everyone's pocket can be enabled for applications like capturing fleeting motion of objects, high bandwidth optical data communication, determining optical flow for objects in motion, and artistic photography. We propose a passive optical accessory that can be fitted to existing CMOS cameras in the market. This optical accessory sees the world in a single line and hence called Monoline camera. We show how this converts an ordinary 25 fps camera into an ultra-high frame rate 25,600 fps camera for a single line. Our hardware prototype consists of an ordinary CMOS camera and an accessory that can be fitted to this camera. Our accessory optical design is created by simple introduction of a cylindrical lens and a single line mask to an aspherical lens, as can be seen in the inside view of the camera. All the light coming from a line in the scene passes through this monoline slit and spreads across the sensor. We exploit the rolling shutter to create an ultra-high frame rate monoline camera. For ease of explanation, we denote the lens plane as UV plane, mask plane as PQ plane, and sensor plane as XY plane. We place the monoline slit in the Q direction, perpendicular to the direction of rolling shutter. The method of image acquisition in CMOS cameras is through a rolling shutter. Here, each frame is captured by exposing and reading out different portions of images at different instances of time. We exploit this principle of rolling shutter to read out a single line across time to capture and analyze sweeping motion of objects. Consider a scene consisting of a multicolored object in motion. The monoline slit, which is placed at the focal length of the aspherical lens, perpendicular to the rolling shutter, allows all the energy from the line MM1 on the scene to pass through. Since the sensor is kept at combined Y focus of the aspherical and cylindrical lens, we get focused copies in the Y direction on the sensor. In the X direction, the light spreads across and creates multiple copies on the sensor. This blur is because of the distance of the sensor from the mask. Thus, the energy spreads across the sensor to produce an anisotropic blur on the sensor, that is, focused image of the line MM1 in Y direction and multiple copies of this line in X direction. At time instance t1, a line MM1 cutting across pink and blue regions of the object is captured at the first column of the rolling shutter sensor. At time instance tn, the object has moved and the same line MM1 now cuts across yellow and green regions of the object, and it is captured at the last column of the sensor. This is possible because rolling shutter reads different columns at different time instances. Our software simulations were done in MATLAB and Zemax. We now show how monoline camera can be used to analyze geometry of objects in motion. The scene depicted shows a set of moving cars on a street. Here, the monoline camera captures one line of this scene. We can see the output of monoline camera capturing the sweeping motion of the cars alone. From the geometry of the cars, we determine which car is moving the fastest. The fastest car will appear for the least time on the single line and hence will appear the shortest. We now introduce a dual line mask and show how it can be used to determine optical flow for objects in motion. We see a cyclist moving across the street. A mask with two lines L1 and L2 is used to capture this scene. The cyclist will appear at different time instances on the two lines in the scene. So, the position of the cyclist will be different for each of the outputs obtained on L1 and L2. This difference denotes the time taken for the cyclist to move from one line to another, from which we can determine the optical flow for the cyclist in motion. Our hardware experiments were done with monoline camera accessory attached to Thorlab's CMOS sensor. We now show how monoline camera can be used for optical data communication. We can see three LEDs each transmitting different information. The Thorlab sensor has 1024 rows and 1280 columns. Each LED can transmit 1 bit for each of the 1024 rows on each captured frame, and this can be decoded by the sensor. At 25 fps, this means that each LED can transmit 25,600 bits per second. Potentially, there could be one LED for each column in the sensor, simultaneously transmitting data, thus enabling high bandwidth optical data communication. Theoretically, 31 megabits per second of data can be transferred with our setup. A perfectly focused setup would have created only one line per LED onto the sensor. However, here we see multiple columns for every LED because of imperfections in cylindrical lens. We now show monoline camera output for a high-speed rotating fan. For a high-speed moving fan, normal cameras cannot distinguish blades when the fan is rotating at such high speeds. Monoline camera views one line of the scene through the single line mask. This line in the scene cuts across blue blades, yellow center and yellow stand of the fan, and this can be seen in the output frames where we see each individual fan blade. We now show monoline camera output for a high-speed rotating fan with 24 spikes. Here, we introduce 24 Bayer spikes to the fan. To capture all the 24 spikes while the fan is rotating at high speed, we would need a camera with minimum 600 fps frame rate. We show that our monoline camera is able to capture all the 24 spikes of this fan. We now show how we can estimate relative optical flow of objects in motion with monoline camera. We can see a toy object being thrown twice, at first slowly and then faster. In both cases, shadows are analyzed by our monoline camera. By analyzing the geometry of the shadows in the output frames of the monoline camera, we can calculate the relative optical flow of the object in motion. The toy object, when moving faster, has a shorter shadow than when it is moving slower. The slower moving shadow covers 360 lines on the sensor. The faster moving object covers only 300 lines. We can therefore have high accuracy in estimating relative optical flow using our monoline camera. Monoline camera can enable wide variety of consumer, industrial and medical applications. It can be used in high-speed photography applications that require capturing or analyzing sweeping motion of objects like blood flow, fast-moving vehicles, etc. It can be used in gesture-based gaming applications which may require accurate calculation of optical flow information. It can be used in creative fun applications that give an artistic tinge to the captured photographs. It can also be used for high bandwidth optical data communication. In future, we would like to explore user adaptive roles where at runtime we can dynamically change which rows in sensor can be configured for the next time capture. For any scene, we can get a variety of interesting outputs by reading out either one line of the sensor or a region of interest, as well as lines in any random order. With such a feature, a captured scene can be interpreted and analyzed in many ways. In future, we would like to explore monoline camera as a mobile phone accessory. For monoline camera feature to work as a mobile phone accessory, optical design has to be tuned to work in conjunction with already existing lens package of a mobile device. With over 1 billion cameras on the market, we believe our passive optical accessory can cater to a wide variety of